Good morning, welcome to problem session 4. Today we start with the problem 38. Find the Fourier cosine transform of f of x equal to 1 by 1 plus x square. Using this, find the Fourier sine transform of x by 1 plus x square. First of all, we are going to find Fourier cosine transform of this function. Fourier cosine transform of omega is equal to root of 2 by pi integral 0 to infinity f of x cos omega x dx. I denote this as capital I. Capital I is equal to root of 2 by pi into our f of x is 1 by 1 plus x square integral 0 to infinity 1 by 1 plus x square cos omega x dx. Now this integration is not easy because one of the integrand is 1 by 1 plus x square. We cannot directly calculate this using integration by parts. So we make some mathematical manipulation. I just take derivative of this I with respect to omega. So di by d omega is equal to root of 2 by pi integral 0 to infinity 1 by 1 plus x square into derivative of cos is minus sine. I take minus outside sine omega x into derivative of omega x with respect to omega, that is into x dx. I put this x into numerator of 1 by 1 plus x square. So I got minus root of 2 by pi integral 0 to infinity x by 1 plus x square sine omega x dx. Now I make some adjustments in the numerator and denominator. I write numerator as x square, so we have to divide the denominator by x. So x square and x get cancelled, I got x back. I rewrite x square as 1 plus x square minus 1, and I take term by term division here. I get minus root of 2 by pi integral 0 to infinity 1 plus x square minus 1 the whole divided by x into 1 plus x square sin omega x dx. Apply term by term division. I got 1 plus x square divided by x into 1 plus x square. So this 1 plus x square and 1 plus x square get cancelled. I got 1 by x into sin omega x. I write 1 by x here. Next term is minus 1 by x into 1 plus x square, minus 1 by x into 1 plus x square into sin omega x dx. Now we multiply the sin omega x into these terms. So 1 into sin omega x by x, integration from 0 to infinity, then minus into minus plus root of 2 by pi integral 0 to infinity sin omega x into 1 by x into 1 plus x square, that is 1 by x into 1 plus x square into sin omega x dx. But we are familiar with this integral. All these manipulations are to get this integral here, because we know integral 0 to infinity sin omega x by x dx is pi by 2. I can replace this integral by pi by 2. That is next step. Minus root of 2 by pi into this integral become pi by 2 plus root of 2 by pi integral 0 to infinity 1 by x into 1 plus x square sin omega x dx. On simplification, I get minus root of pi by 2 plus root of 2 by pi integral 0 to infinity 1 by x into 1 plus x square sin omega x dx. I take one more differentiation with respect to omega. That means differentiate this with di by d omega. This is di by d omega with respect to omega once again. D square I by d omega square is equal to derivative of this constant equal to 0 plus root of 2 by pi integral 0 to infinity, only sine terms contains omega. I take derivative of this sin omega x. So 1 by x into 1 plus x square into derivative of sine is cos omega x into derivative of this omega x with respect to omega, that is into x dx. So this x and x in the denominator get cancelled. So I get root of 2 by pi integral 0 to infinity 1 by 1 plus x square cos omega x dx. This is nothing but Fourier cosine transform of 1 by 1 plus x square. That is our starting point. Fourier cosine transform of 1 by 1 plus x square is denoted as I. So d square I by d omega square becomes I. So we got a differential equation that implies d square I by d omega square minus I is equal to 0. This is a differential equation of I with respect to omega. So I denote d by d omega as capital D. So this can be written in symbolic form as d square minus I operates on I equal to 0. This I stands for identity operation or 1. The solution, this is a homogeneous ODE. To find the solution, we have to find IH. It has only IH. For that, I take the auxiliary equation m square minus 1 equal to 0. When I factorize this, I got m plus 1 into m minus 1 equal to 0. So roots are m is equal to 1 and minus 1. So using the solution method of ODE, I can write I is equal to C1 e raised to m1x. Here in the stead of x I have omega, C1 e raised to m1 omega plus C2 e raised to m2 omega. Here m is 1, so C1 e raised to 1 omega plus C2 e raised to m2 is minus 1, so minus 1 omega or minus omega. So this is our I means Fourier cosine transform, but we have to find these C1 and C2 because they are arbitrary constants. For that I am going to use the initial condition omega is equal to 0 in I and di by d omega. We know I is equal to root of 2 by pi integral 0 to infinity 1 by 1 plus x square cos omega x dx. I put omega equal to 0 there, so I got cos 0 into x, that is cos omega x becomes cos 0 into x. Cos 0 is 1, so root of 2 by pi integral 0 to infinity 1 by 1 plus x square dx. And also we put omega is equal to 0 in this expression. I got c1 into 1 plus c2 into 1 because e raised to 0 is 1, that is left side. But we are familiar with this integral 0 to infinity 1 by 1 plus x square dx is tan inverse x with the limit 0 to infinity. When I put upper limit tan inverse infinity minus lower limit tan inverse 0. Tan inverse infinity is pi by 2 and tan inverse 0 is equal to 0. So this expression becomes pi by 2. When I simplify root of 2 by pi into pi by 2, I got root of pi by 2. The left side is c1 plus c2. I use omega equal to 0 here. From here I got I of 0 is equal to c1 plus c2. So I got one equation in c1 and c2. I use the same thing in di by d omega. For that I start with I is equal to c1 e raised to omega plus c2 e raised to minus omega. That is our solution. Now di by d omega of this expression is c1 e raised to omega plus c2 into derivative of e raised to omega is e raised to minus omega into minus 1. That minus 1 becomes here positive to minus. Again di by d omega is equal to minus of root of pi by 2 plus root of 2 by pi into integral 0 to infinity 1 by x into 1 plus x square sin omega x dx. This is an intermediate step. I will show that step. In the previous page we have derived this. This is di by d omega. This step is di by d omega. It contains sine term, integral and this constant. When omega is equal to 0, this expression, this integral goes to 0. We got minus root of pi by 2. That is the second step to find another equation involving c1 and c2. Why we take this more equation? The reason is this equation contains two variables. To get solution of the c1, to get values of c1 and c2, we have to get at least two equations in two unknowns. Then only we can find distinct values for the c1 and c2. So di by d omega is equal to this expression. Then omega is equal to 0 in this 39 and 40. Here it becomes c1 minus c2, that is left side. Then this right side becomes di by d omega with omega equal to 0 goes to minus root of pi by 2. So we got two equations. This is the equation. Now we have two equations in two unknowns. Two equations in two unknown can be solved uniquely. Here it is very easy because when we add these two equations, c2 get cancelled. c2 minus c2 becomes 0 and 2c1 is equal to 2c1 is equal to 0. 2c1 is equal to 0. Right side is also root of pi by 2 minus root of pi by 2, we go to 0. So c1 equal to 0. When we subtract the second equation from first one, so c1 minus c2, that goes to 0. c2 minus c2, that is 2c2 is equal to root of pi by 2 minus root of pi by 2, that is 2 into root of pi by 2. So we got c2 is equal to root of pi by 2. That is the solution steps. So we got c2 equal to root of pi by 2, c1 equal to 0. So we substitute these c1 and c2 in this expression. C1 and c2 in this expression. C1 becomes 0, c2 is equal to root of pi by 2. So I is equal to root of pi by 2 into e raised to minus omega. That is our next step. That is Fourier cosine transform of omega, that is denoted by capital I, is equal to root of pi by 2 e raised to minus omega. Now we have to find the Fourier sine transform of this function. Start from the Fourier sine transform definition. Fourier cosine sine transform of f of x is equal to root of 2 by pi integral 0 to infinity f of x sin omega x dx. This is definition. I put f of x here, that is equal to root of 2 by pi integral 0 to infinity x by 1 plus x square sin omega x dx. From the previous step in Fourier cosine transform definition, this integral can be written as minus di by d omega. I will show you that step. this step. Di by d omega is equal to minus root of 2 by pi integral 0 to infinity x by 1 plus x square sin omega x dx. This expression with the difference in minus is now fs bar of omega. This is Fourier cosine sine transform of this function. Fourier sine transform of this function. Additionally, there is a negative. We put this negative to the left side. So the Fourier sine transform of this function x by 1 plus x square is equal to minus of di by d omega. We are going to use that. Minus di by d omega. So di by d omega, we have written di by d omega is c1 e raised to plus omega minus c2 e raised to minus omega. This minus is this minus. So when we put c1 equal to 0 here, this term goes to 0. c2 is equal to root of pi by 2, but minus into minus positive, so plus root of pi by 2 into e raised to minus omega. That means we got this result. Fourier cosine transform of 1 by 1 plus x square is root of pi by 2 into e raised to minus omega, and Fourier sine transform of x by 1 plus x square is same thing, root of pi by 2 into e raised to minus omega. So that's about this problem. This problem is very important in exam point of view, because we have to remember 2 or 3 important steps. If we miss the steps, we cannot solve this problem. One is the manipulation, differentiation with respect to omega. Then we multiply numerator and denominator by 1x. Then x square in the numerator can be rewrite as x square plus 1 minus 1. Then term by term division. All these are to get the integral 0 to infinity sin omega x by x dx. We can rewrite that integral using the definition integral 0 to infinity sin omega x by omega is equal to pi by 2. That is the key step. So that's all about this problem.